Good morning and most welcome to 1301, 1301 of the Heidegger series. And we will take a look at affordances today, because they are fitting pretty well, I understand, together with Lee Smolin and Roberto Unger's new vision of the universe, and where objects become obsolete, human artifacts that doesn't serve a purpose. Instead, there is a floating line between the two poles where everything happens, anything that is real. In the potential and the actual, and on top of that, especially in between actual and potential. This is where it becomes, so to speak. I will begin today with an article by Diane Pecher from the Erasmus University in Rotterdam. The role of motor affordances in visual working memory. And I will then continue with the mental affordance hypothesis by McClelland. He has an hypothesis that also thinking is a type of affordance. And I am amazed how similar all of this is, in different words, in different concept, and from a different perspective, but still very similar to the vast project of Lee Smolin and Roberto Unger. So I begin. The role of motor affordances in visual working memory. Abstract. Motor affordances are important for object knowledge. Semantic tasks on visual objects often show interactions with motor actions. Prior neuroimaging studies suggested that motor affordances also play a role in visual working memory for objects. When participants remembered manipulable objects, e.g. hammer, greater premotor cortex activation was observed than when they remembered non-manipulable objects like a polar bear. In the present study, participants held object pictures in working memory while performing concurrent tasks such as articulation of nonsense syllables and performing hand movements. Although concurrent tasks did interfere with working memory performance, in none of the experiments did we find any evidence that concurrent motor tasks affected memory differently for manipulable and non-manipulable objects. I conclude that motor affordances are not used for visual working memory. Imagine that you are performing a complicated task, for example, preparing a meal or fixing a bike, which involves manipulating various objects. Your performance would be very efficient if you could start preparing actions before you looked at the objects. As you are stirring the sauce, you can already start planning to grab a knife with one hand and a tomato with the other hand. You may even take the future action of cutting the tomato into account so that the knife is in your dominant hand with the blade facing down. Such planning would involve working memory in which the objects that are currently out of the field of vision are kept active. In this paper, I will review research that investigated whether working memory also retains affordances for those objects. Grounded cognition. Recent theory of cognition proposed that the elements of thought are not words or symbols, but visual and motor images. According to this grounded cognition view, thinking shares resources with perception and action. When a person thinks about an object, such as a tomato, earlier experiences with tomatoes are reactivated. This reinstatement of earlier activation results in a sensory motor simulation. The visual system simulates seeing a tomato. The motor system simulates the acts of grasping, cutting, and eating a tomato. And the olfactory and gustatory system simulates the smell and the taste of the tomato. Thus, thinking about a tomato, the brain acts partially if the person is actually perceiving and interacting with the tomato. Rather than an exact replica of experiences. However, these patterns are distorted and represent only partial experiences. In Barcelou's 99 theory, simulators capture patterns of activation for a particular category of experiences. As a result, they represent a distributed pattern of experiences with a concept such as tomato. Simulation of experiences is dynamic and flexible and can even represent imaginary events. Two, one, perception and cognition. Research has shown that representations are organized along sensory motor modalities and contain modality-specific information. In perception, switching modalities between trials incurs a processing cost. For example, participants who respond to light flashes and noise burst respond more slowly if the previous stimulus was in a different modality than if it was in the same modality. Pecher, Seelenberg, and Barsalou show that mental representations behave in a similar way. When participants had to verify a property for a concept for example, red for tomato. They were slower in the previous verification. Was for a property from a different modality. For example, loud for blender. Than from the same modality, for example, sparkles for diamond. The same effect was obtained if, instead of verifying a concept property pair, on the previous trial, participants indicated the location of a perceptual stimulus. Such as a burst of noise or a flash of light. Other studies have shown that when language comprehenders read sentences, their mental representation of the sentence meaning is a simulation of the described experience, including visual information that was not directly stated in the sentence. For example, when participants read "the eagle was in the sky," they were able to recognize a picture of an eagle with its wings stretched out more quickly than one with its wings folded in. Whereas the reverse was found if they read "the eagle was in the nest." Such results point out that there is overlap in perceptual features between the mental representation of an object and the perception of that object. The effect of visual overlap was also found when there was an hour-long interval between sentence reading and picture processing. Thus, implied visual features are not only represented during online language processing, but remain more salient after longer delays. Similar effects are found even if the task contains no visual information. When participants are asked to list properties of concepts, they are more likely to name properties that are visible from an implied perspective. For example, seeds is named more frequently as a property of half a watermelon than as a property of a watermelon. Words that refer to objects with similar shapes, for instance, banjo, tennis racket, can prime each other in simple tasks such as lexical decision or word pronunciation. Thus, perceptual features are relevant for concepts during language comprehension, even when readers are not given any instructions to use visual information. Action and cognition. A major role for cognition is to support people's actions in the world. The potential actions that a person can perform on an object are referred to as affordances. Affordances thus provide important information to the observer about the potential actions that can be performed with objects. For example, a cup affords grasping, lifting, and tilting, allowing the user to drink from it. Such motor affordances are proposed to be central to conceptual knowledge. There are two sources for the activation of affordances. First, perception of an object activates its affordance. When a person perceives the physical characteristics of an object, such as its shape and size, the object's affordances are automatically activated. The results suggest that affordances are activated by both perceptual information and knowledge of the object's function. Moreover, studies have found that affordances are activated by words and sentences that refer to manipulable objects or actions, indicating that a direct visual information is not even necessary to activate affordances. Affordances and visual working memory. The question is whether motor affordances also support working memory or short-term memory for objects. As illustrated at the beginning of this paper, in many situations, performance will be better if affordances are kept active in working memory. Working memory might recruit the motor system to maintain such affordances. If the motor system is thus part of working memory, it might also be used in contexts where there is no need for an action plan. Affordances might be activated anyway, and that provide useful information about objects. So using that information might improve memory performance. Several studies have suggested that object affordances are activated automatically when someone sees an object, even if the object is depicted on a computer screen and there is no intention to perform an action with that object. Tucker and Ellis found that semantic categorizations were faster and more accurate when the response script required for categorization was compatible with the object affordance than when it was incompatible. Masson showed that hands' responses were affected by the orientation of a task-irrelevant object's handle, but also by the object's function. This result indicates that the source of such automatically activated affordances is a combination of visual and semantic information. On the other hand, some studies have questioned whether such effects are caused by activation of affordances or might be due to more abstract correspondences between visual stimuli and the manual response. For example, effects that show facilitation when an object affords a grip with the same hand as used for responding, compared to when it affords a grip with the opposite hand, might also be explained by abstract spatial codes. Thus, there is some debate on whether affordances are activated automatically. If they are, however, working memory might use them to maintain objects. Research has indicated that the motor system is recruited by working memory when the task requires motor information. When participants have to keep actions in memory, the motor system seems to be involved. Concurrent motor tasks interfere with working memory for actions, especially when they focus on the same aspect of actions. A role of the motor system in working memory has also been suggested by neuroimaging studies that obtain activation of the premotor cortex during visual working memory tasks. However, most of these results might be due to response planning during the retention interval. Because tasks typically require tapping or pointing to spatial locations as a response. Nonetheless, these findings might also indicate that the motor system was recruited for memory retention, maintenance. Did not observe any differences in the fMRI, the functional magnetic resonance inference. Bold response between spatial and object working memory, suggesting that the same processes underlie memory for these different types of information. A study by Mecklinger, Grunewald, Weisskopf and Dollar found activation of premotor cortex in a working memory task for manipulable but not for non-manipulable objects. Since manipulable objects have affordances, whereas non-manipulable objects do not, these results strongly suggest that affordances are recruited for working memory. Some caution is needed when one interprets such findings. However, because fMRI results that are mostly correlational cannot show whether activated regions are necessary to perform a task, nor do they show that a particular process was recruited. When researchers observe brain activation in overlapping areas between two tasks, they tend to conclude that the tasks must share a functional component. Such a conclusion is only valid, however, if brain regions are involved in only one particular function. And we know that this is not the case. When researchers still draw conclusions about function from activation in certain brain areas, might just as likely be the result or a mere side effect of behavior. A similar point has been made about behavioral studies that showed effects of semantic processing of objects on motor responses. These effects might show only co-activation of affordances during or after processing semantic features of the object. Thus, even though affordances have been activated, they might not have contributed to the semantic representation of the object, but might merely be a byproduct of semantic processing. Therefore, activation of a brain area that is also involved in the motor tasks is not sufficient to conclude that motor simulations support working memory. Evidence from interference studies, however, has indicated that language processing and learning are supported by the motor system. In these studies, a concurrent task that occupies the motor system is shown to affect cognition. For example, Busiello et al. Found reduced repetition priming for actions when participants concurrently performed a hand motor task compared to a verbal task. This finding indicates that the motor task interfered with creating a memory representation and thus suggests that mental representations for actions rely on activation of motor affordances. Castile argued that whether action and conceptual processing interfere depends on the timing of the two processes. In particular, when the two are performed in parallel, they result in interference. Ruschemeyer et al. Show that such interference effects occurred when participants performed intentional actions, but not when they performed passive actions. That is, when the finger was forced to move by a device. Interference effects on performance provide evidence that motor affordances contribute to comprehension, because they show that when it is harder to activate motor affordances, comprehension suffers. Investigating the role of affordances in working memory. Study 1. Interference paradigms have also been used to investigate whether the motor system and working memory performance are causally related. In our lab, we have investigated the role of the motor system for visual working memory. In the first study by Pecher, photos of manipulable pliers and non-manipulable objects like road signs were presented in a working memory task. McClelland et al. Found differences in premotor cortex activation between manipulable and non-manipulable objects, and argue that because manipulable objects have affordances, the motor system was recruited to maintain these objects in memory, whereas non-manipulable objects have no affordances, and therefore the motor system would not be recruited. Because of this difference, a concurrent motor task would be expected to disrupt memory performance more for manipulable objects than for non-manipulable objects. In the working memory task, an object was presented briefly, followed by a 5-second retention interval, during which participants had to keep the objects in memory. Then the test stimulus was presented, and participants indicated if the test object was the same as the study item. Only a small set of objects was presented repeatedly in the working memory task to prevent contribution from long-term memory. When objects are repeated often, they all become very familiar, and subjects have to actively maintain the object in working memory in order to perform the task. The role of the motor system was investigated by having participants perform a concurrent motor task. In this task, participants made a fist and then stretched their fingers one by one. A motor task like this, which keeps changing the hand configuration, should be most likely to interfere with grasping and other types of object-directed actions. Moreover, because the task is dissimilar to any interactions with any of the objects, the results would not be complicated by differences in congruencies between affordances and motor task. Because the motor task would make it harder to recruit the motor system for memory, participants might change their strategies. In particular, they might use verbal encoding so that they could maintain the object in memory by repeating its name. In that case, any difference between manipulable and non-manipulable objects might disappear. To prevent a verbal strategy, participants were also instructed to repeat a series of 4 nonsense syllables during some blocks of the experiment. Thus, in different blocks of trials, participants performed no concurrent task. The motor task, the verbal task, or both tasks, while they were doing the working memory task. Whereas all these tasks decreased performance in general, the motor task did not affect memory for manipulable objects more than for non-manipulable objects. neither when only the motor task was performed, nor when the verbal task was also performed. Such an interaction was predicted if participants had used motor affordances to maintain the objects in working memory. Because motor affordances can support memory for manipulable objects more than for non-manipulable objects. Although the concurrent tasks influenced performance, the memory task motor task might have been too easy to show the interaction between motor task and manipulability. In several follow-up experiments, the study trial showed 4 rather than just one object. And participants had to keep all 4 objects in memory during the retention interval. However, the results again did not show an interaction between motor task and manipulability. These results indicated that visual working memory does not rely on the motor system. It is possible that participants used mostly visual information to retain the objects in memory. To investigate whether removing this reliance on visual information might push participants toward using affordances. a visual interference task was used. In this task, participants saw an array of many colored blocks that changed color randomly during the retention interval. The results showed again no interaction between motor task and manipulability. In short, in 5 experiments, Pecher did not find any evidence that a concurrent motor task had a larger effect on memory for manipulable than non-manipulable objects. Study 2. In a second study, we further investigated the effect of motor interference using a different measure of working memory. In the previously described study made by Pecher, difficulty was varied by manipulating the numbers of items on the study trial from 1 to 4 between experiments. The effect of increasing the number of items was not just an increase in memory load, however, but also a visually more complex study trial. Moreover, the question is to what extent affordances for each object will be activated if 4 objects are presented simultaneously. Thus, in the easier conditions, motor affordances might not have been used to keep the object in memory, because the task was easy and could be performed visually. And in the difficult condition, motor affordances might not have been activated because 4 objects with different affordances were presented at the same time. In order to exclude these potential problems, Pecher et al. Used the N-back task, in which a series of items is presented individually and participants indicates whether an item is repeated at a distance lag of n trials. For example, in a 2-back task, the sequence might be pliers, paperclip, pocket knife, paperclip, stock, pot, and pliers. The second occurrence of paperclip would be a target repetition, because it occurs 2 steps from the first occurrence. But the second occurrence of pliers is farther than 2 steps and would not count as a target repetition. The N-back task is popular working memory task in neuroimaging studies. An advantage of using this task is that one can easily manipulate memory loads without changing the visual information or response requirements. Moreover, when objects are presented individually, there is enough opportunity for activation of motor affordances for each object. In one experiment, we presented photographs of familiar manipulable and non-manipulable objects. The same concurrent motor and verbal tasks as in Pecher were used. The results show decreased performance with increasing lag. Confirming that the memory task became harder as more items needed to be maintained. As in the previous study, the concurrent tasks affected performance in general, but there was no interaction between the motor task and object manipulability. To further decrease the role of verbal rehearsal, in a second experiment, we used novel objects taken from Taylor and Swan. The manipulable object was a smooth sphere that looked graspable, and the non-manipulable object was a spiked sphere that did not look graspable. If participants cannot use verbal labels to maintain stimuli in memory, they should rely more on other types of information. Thus, it would be more likely that affordances were used to maintain the spheres in memory. To further promote participants' reliance on affordances, we varied the spheres in size only, in order to distinguish between different stimuli. Participants thus needed to keep the size of the spheres in working memory. As size is strongly related to grip, support from affordances would greatly enhance working memory performance. Therefore, if there are circumstances in which affordances play a role, this should be a strong case. However, again, there was no interaction between the motor task and object manipulability. Study 3. A reason for this lack of support for the motor system might be that in both studies discussed so far, the concurrent motor task was only interfering with affordances. That is, the motor action that was required by the task was incompatible with any potential interaction with the objects. One could argue that in such a case, participants may have stopped paying attention to the motor system, because any attention to the motor system would have hurt performance. Therefore, in a third study, Quake et al. Changed the concurrent motor task so that the action was congruent with one set of items and incongruent with another set of items. The concurrent task was to squeeze a rubber cylinder between blocks we manipulated, whether the cylinder was large and held by the entire hand, so-called power grip, or small and held by between the thumb and the index finger. If object affordances were used for memory, memory for objects should be better if the concurrent task was congruent with the object's grip than if the concurrent task was incongruent with the object's grip. The results of this study show that, like in the previous studies, although the concurrent task did interfere with memory performance in general, there was no difference in performance between congruent and incongruent conditions. Conclusion. In summary, the results from these 3 studies do not confirm that motor affordances are used to support working memory. If participants had used motor affordances for manipulable objects, we should have obtained interactions between objects' manipulability and motor interference. But the data did not provide any evidence for this, because many researchers might be wary of drawing conclusions from null findings. We also performed Bayesian tests, which can be used to evaluate whether the data provide more evidence for the null or the alternative hypothesis. These analyses showed that the data provided positive to strong evidence for the null, that is, the absence of an interaction. This conclusion was the same under different circumstances, such as different difficulty levels, whether there was verbal interference, visual interference for familiar and novel objects, and even when the motor task could have been helpful. Thus, the conclusion is that the motor system does not support visual working memory. It might be argued that we simply failed to interfere enough with motor affordances to find differences between manipulable and non-manipulable objects, or between congruent and incongruent objects. This would be inconsistent, however, with other studies that have used similar tasks, such as squeezing a rubber tube or sequentially touching the head, shoulders, and hips with both hands. In studies on working memory for actions, such tasks have been shown to affect performance. Our tasks were similar in nature and difficulty as those used by these other studies. Therefore, it seems unlikely that they were not strong enough to cause interference in the motor system. The absence of a role for motor affordances in visual working memory should not be taken to indicate that motor affordances play no role at all in cognition. Indeed, there are many situations in which motor affordances and cognition interact. As mentioned above, several studies have shown effects on motor interference on working memory for actions. These results suggest that the motor system is recruited when the task explicitly requires people to remember actions. Second, as discussed earlier, many studies have shown a role of affordances in tasks that require semantic or conceptual knowledge. This suggests that conceptual knowledge includes the actions that can be performed with an object and is activated even under circumstances that do not require action execution. Thus, object affordances have a role in cognition, at least under circumstances that require explicit action knowledge or deeper conceptual knowledge. Visual working memory, however, might not rely so much on conceptual knowledge. In general, working memory seems to depend mostly on the modality of the items that are remembered. This is consistent with many studies showing that interference effects in working memory depend on similarity in terms of surface features rather than meaning. In the present study, the stimuli were presented visually, which may have resulted in memory representation that were mostly visual. One might think that the conclusion that visual working memory is not supported by the motor system is inconsistent with the fMRI findings that showed activation of the premotor cortex during working memory maintenance of manipulable objects. These fMRI findings might be explained by different mechanisms. However, first, it's possible that participants in McClelland et al. Study were using long-term memory to perform the task. Performance in short-term memory tasks is actually the result of both short-term and long-term memory retrieval. Because McClelland et al. Presented many different study items, this resulted in many trials on which both study and test items were new. That is presented for the first time during the experiment. Therefore, long-term familiarity alone would have been a good indicator of whether the item was a target, that is familiar, or a distractor, unfamiliar. To prevent long-term memory retrieval, we used only a small set of items, so that familiarity alone was not an indicator of whether the item had been presented n trials back. Second, their results might have been caused by just the visual presentation of the object and could have been unrelated to the memory task. McClelland et al. Found that presentation of the same objects in passive viewing task also activated the premotor cortex. Thus, the observed activation during the working memory task could have been simply a byproduct of seeing the objects rather than an indication of support from the motor system. In contrast, by looking at actual performance, we were able to show that affordances do not contribute to memory. Our results illustrate that the interpretation of brain imaging results is quite complicated and has to be done with caution. Imagining results are often correlational and therefore cannot tell us whether activation reflects core, necessary processing, or mere byproducts of processing. Moreover, because brain regions are parts of larger networks and are used by multiple processes, activity in a brain region cannot be used to conclude that a specific process was going on. In this particular case, activity in the premotor cortex during a working memory task had been interpreted as showing the involvement of affordances. But our results indicate that this was probably a logical fallacy of affirming the consequent. With the interference method used in our studies, we can look at the causal relation between affordances and memory performance. And we conclude that affordances do not support visual working memory performance. So that was the finish of that 13 pages by Diane Pecher, and she takes a negative stand to the idea of motor affordances being part of visual working memory. And I think this rather bit easier article gives us a chance to get into the subject a bit more. Now it will become a little bit more heavy, but less of experiments though. So we go over to Tom McClelland. And the article is called The Mental Affordance Hypothesis. I will put the paper in the description. I'm just going to write Tom McClelland. Our successful engagement with the world is plausibly underwritten by our sensitivity to affordances in our immediate environment. The considerable literature on affordances focuses almost exclusively on affordances for bodily actions such as gripping, walking, or eating. I propose that we are also sensitive to affordances for mental actions such as attending, imagining, and counting. My case for this mental affordance hypothesis is motivated by a series of examples in which our sensitivity to mental affordances mirrors our sensitivity to bodily affordances. Specifically, subjects perceive opportunities to perform a mental action, and their doing so leads, under the right conditions, to the automatic preparation of that action. I conclude by sketching a mental affordance research program that would reinforce my case for the mental affordance hypothesis and establish its ramifications for a number of debates across philosophy and psychology. Introduction. Affordances are opportunities for action. A teapot, for example, has the property of being grippable. When a subject grips the teapot, she exploits this affordance. The concept of affordances, introduced by the ecological psychologist J.J. Gibson, has been applied extensively across a range of disciplines. There are compelling reasons to think that our sensitivity to affordances plays a crucial role in action. Throughout the considerable literature on affordances, the afforded actions that theorists discuss are, with only a few exceptions, bodily actions such as gripping, walking, or eating. This paper presents the hypothesis that we are also sensitive to affordances for mental actions, such as attending, imagining, and counting. Although this mental affordance hypothesis is ultimately answerable to empirical evidence, a variety of phenomenological and theoretical considerations strongly suggest that we are appropriately sensitive to opportunities for mental actions. Although there are few proposals in the literature that resembles this claim, as of yet nobody has made a general case for thinking that we are sensitive to affordances for mental action in much the same way as we are sensitive to affordances for bodily action. The current paper is intended to remedy this. The next section describes how to characterize affordances in general and mental affordances in particular. The third section describes our sensitivity to affordances for bodily action. Specifically, we perceive affordances for bodily action, and our doing so will, under the right conditions, potentiate, that is, automatically prepare the performance of that action. The fourth section pins down MAH as the thesis that there are affordances for a subject S to perform a mental action phi, such that 1. The affordance to phi is perceptible by S, and 2. When S perceives that affordance under the right conditions, the act of phi-ing is automatically readied. The fifth section introduces a series of cases that plausibly confirm that hypothesis. Affordances to attend, affordances to imagining, and affordances to count. I conclude by sketching a mental affordance research program that would reinforce my preliminary case for MAH, which is the mental affordance hypothesis, and establish its ramifications for a number of debates across philosophy and psychology. What are affordances? Gibson introduced the term affordance in his 1966 work, The Senses Considered as Perceptual System, and I seem to be of equal age as that book. His understanding of the concept evolved throughout his career, and his most fully developed account of affordances can be found in his final work, the ecological approach to visual perception. In this book, he introduces the concept as follows. The affordances of the environment are what it offers the animal, what it provides or furnishes, either for good or ill. The verb to afford is found in the dictionary, but the noun affordance is not. I have made it up. I mean by it something that refers to both the environment and the animal in a way that no existing term does. Although the notion of affordances remains a key concept in the ecological school of psychology, it has also been taken up across a wide range of other disciplines, including cognitive psychology, neuroscience, music, anthropology, and artificial intelligence, not to mention phenomenology, for example, Dreyfus, and philosophy of perception. Although the ubiquity of the concept of affordances gives us a vast and diverse body of research from which to draw, it comes at a cost. The term affordance has become weighed down by the theoretical baggage of its different applications. If we strip away the accrued theoretical baggage, affordances are at their core opportunities for action. An opportunity to perform an action is a situation in which it is possible for a subject to deploy some ability they possess. Consider a tree's property of being climbable by me. Affordances are relativized to particular subjects. Thus, what is climbable for me will differ from what is climbable for you, which will in turn differ from what is climbable for a squirrel. For a tree to be climbable for me is for it to stand in a certain relation to my ability to climb. It must be something toward which I can successfully deploy that ability. And I think here you see the likeness between Smolin and Unger very clearly. And not having affordances will leave reality, and we enter into the Newtonian paradigm. Some trees would stand in this relation to my climbing ability. for example, sturdy trees with plenty of branches, and other trees will not. The tree's climbability and my ability to climb the tree's climbability and my ability to climb are complementary disposition. They are a mutually dependent pair of dispositional properties. Look here. Much like a sugar cube's disposition to dissolve in my tea, and my tea's disposition to dissolve the sugar cube. I think it became obvious now, hopefully. I think it becomes obvious also why the Newtonian paradigm is not even true on the intermediary scale. What constitutes an opportunity for action will depend on how one conceives action. Although no shared conception of action can be explicitly found in the affordance literature, I will assume the plausible view that actions are those things a subject does that are under her intentional control. To have control over something you are doing is to be able to continue or terminate it at will. This motivates the following definition of action offered by Levi. Action. Necessarily, A is an action by agent S at a time. T, if and only if S has the specific ability at T to intentionally and directly stop and continue to the event identical with or partly constitutive of S's A-ing, actioning. If you move your leg because you intend to, then this movement is one over which you have exercised control and is thus an intentional action. If you move your leg because a doctor taps your knee with a hammer, then this movement is outside of your control and thus not an action. Instead, it is a mere movement. There is a third category of events that are controllable but not actually controlled. These are non-intentional actions. When you absent-mindedly jiggle your leg, for instance, you are not exercising control over that moment. That said, you could stop the movement if you wished. Actions are complex events with many layers, and an action can still qualify as being under intentional control, even if there are parts of that action that are not controllable by the agent. Gripping a teapot, for example, is an action under my control, even if the exact aperture of my grip is the result of an automatic process outside my control. Unlike some competing views, this account avoids an excessively narrow view of what qualifies as an action. And I think that could be a perfectly legit place to stop. So we can end in this view here. This is where it's happening. This is the position of the self and the world. Claiming that the world is here and the self is here is the Newtonian paradigm, the one that we're presently at. And all thinking sort of centers on all writings the last 3 centuries. There is no position here. This is forever expanding. So is this one. There's not stop here. So the Newtonian paradigm are effectively randomizing both self and the world. Both gets lost at the same time, or more lost. It's a scale, of course. And here we have the name of the author, Tom McClelland, and earlier we had Diane Pecher, or Pecher. I think I end exactly with this one.